This is the practice test review for the test on gas laws. First question, which of the following statements is correct? Liquids typically have lower density than gases. No, the opposite of that would be true. So that's not the answer. The pressure of a gas is inversely proportional to the temperature of the gas. No, the pressure and the temperature are directly related. The partial pressure of a gas is not affected by the composition of the gas. That is the correct answer. Partial pressure of a gas is independent of the composition of the gas. It doesn't matter what the gas is made of. All gases have the same partial pressure at the same temperature and volume. Which of the following describes Charles's law? Charles's law is the relationship between volume and temperature. So we're looking for an answer that has volume and temperature in a direct relationship, which means they change in the same way. As the temperature of a gas increases, its volume increases. Well, that is a direct relationship between pressure and volume, so the correct answer here was A. Number 3, there was actually a typo here. This should say, which of the following is correct? The volume of a gas is inversely proportional to its pressure. Well, that's correct. The total pressure of a gas in a container is equal to the sum of the partial pressures of its component gases. That's also correct. And the pressure of a gas is directly related to its temperature is correct. So in fact, all of these responses are correct. What causes a balloon to shrink on a cold day? And you're going to need to write a bit of an explanation, and you can use diagrams. I'm not going to write the whole thing out, but I will explain it and do my best to draw a diagram that shows what I'm saying. So a balloon, when it's filled up, has a certain number of particles pressing out against the side with a certain amount of force, depending on the temperature. And at the same time, there are air particles pressing in with an equal amount of force once the balloon is inflated. So the pressure inside and the pressure outside are the same, which allows the balloon to hold its shape. The pressure applied by the particles inside and outside the balloon is determined by the temperature, the number of particles, and that all in turn determines the volume. Well, when you take that balloon outside and the particles outside are already at a certain temperature, but they're at the same pressure as the particles that were inside. So they're putting in the same amount of pressure to the outside of the balloon. However, the particles inside the balloon are now going to slow down. So they are now pushing off less force because they're moving less. So now you have this mismatch between the internal pressure, which has gone down, and the external pressure, which has stayed the same. That causes, or that allows, the external particles to push the balloon in, which causes the volume to go down, which causes it to shrink. So the volume and the temperature, that's Charles's law. As the temperature goes down, the volume goes down if the pressure is equal. And since in both cases we're at atmospheric pressure, the pressure stays the same, but the temperature drops, which is why the volume also goes down. How does a suction cup work? Again, I'm going to use a diagram while I explain what you would roughly need to write, and obviously it's not word for word what I'm going to say. But we start out with a suction cup, looking something like this, right? And if it's just in the air, right, you've got air particles pushing on it, and let's say, obviously the number of particles is much bigger than what I'm drawing, but just for simplicity, 4. And there's an equal number, or with equal pressure, particles are pushing on the outside, or both sides. Right, so this is the inside of the suction cup on the right, and the outside would be on the left. Now if you take that, and let's say you push the suction cup against the window, you're forcing out a lot of the air particles. So now there are less particles inside, and they're the same amount of pressure being applied from the outside. We haven't really changed the temperature necessarily, but now you have fewer particles that can push back. So the particles inside the suction cup are outnumbered by the pressure, the particles on the outside of the suction cup. So as long as the force from the outside is greater than the force on the inside, then the suction cup is effectively being pushed against the window. Okay, it's being held up by the air on the outside. It's not actually being sucked to the window, it's being pressed against the window by the air outside as opposed to the air inside. Could you drink through a straw on the moon? Well, the short answer here is no. And why not? This is what's really important. Well, the way a straw works, kind of like we've seen in the suction cup example, when you drink through a straw, what you're doing is you're making the pressure inside the straw go down. By increasing the volume of your lungs, you lower the pressure inside. That decreases the pressure inside the straw, and since there's pressure, if we have the liquid here, there's pressure from the air pushing down on the surface of the liquid in the cup, well then that pressure forces the liquid to go toward the area with lower pressure, which is inside the straw. So you're not sucking the liquid up, the air outside is pushing the liquid up through the straw. Well, so that's on Earth. On the moon, there is no air. There's no pressure outside. So it doesn't matter how much you lower the pressure inside the straw. There's no pressure out here to push down on the liquid. So the liquid will never be pushed up through the straw because there's nothing pushing it. So you can't drink through a straw on the moon because there's no air pressure outside to push that liquid up through the straw, no matter how. You can't drop the pressure inside the straw below zero, so there's never going to be that difference between the outside pressure and the inside pressure, which causes liquid to flow up through the straw. Okay, ideal and combined gas laws. So a gas is cooled from 200 to 100 while the pressure is held constant. If the initial volume is 45, what is the final volume? Okay, so we have two temperatures. We have a temperature 1, temperature 2, and we have a volume 1. We need volume 2. That's the question. So this is going to be using Charles's law, which says that V1 over T1 equals V2 over T2. I can plug in the numbers that I have. I have the volume is 45 liters, and the temperature to start with is 200 degrees Celsius. Now we have to add 273 to convert to Kelvin, so it's 473 in Kelvin. And then we've got volume 2 that we're trying to find, and the final temperature is 373 Kelvin, which is 100 Celsius plus 273. So when I do that math out, I end up with 45 times 373 when I cross multiply, and then that's divided by 473 equals V2. If I do that math, I get 35.5 liters. Does that make sense? Well, the temperature went down, which means the volume should also have gone down, and it did. It went from 45 to 35, so that makes sense. An ideal gas has a pressure of 400 millimeters mercury at 270 milliliters and 5 degrees Celsius. If the pressure changes and the temperature changes, what's the new volume? So we've got pressure 1, we've got volume 1, we've got temperature 1. So we have all three variables here. And then we've got a pressure 2 and a temperature 2. We need volume 2. So this is going to be the combined gas law, which looks like this. There should be T1 equals pressure 2, volume 2 over temperature 2. Then we plug in the numbers we're given. The starting pressure is 400. The starting volume is 270. The starting temperature is 5 degrees Celsius, which plus 273 is 278 K. And that equals 140 times V2 divided by the new temperature, which is 50 plus 273, or 323 Kelvin. So when I multiply all that math out, I find that the new volume is 896 milliliters. So you would do 400 times 270 times 323, and then that's divided by 278 times 140, and that gives you V2. What is the volume of 52 grams of nitrogen at 100 Kelvin and 1 atmosphere? Well, we don't have a formula that includes grams, but thinking back a little ways, we can convert grams to moles if we know the molar mass, and we do have a formula called the ideal gas law, which has the number of moles in it. So if I can convert the grams to moles, then I can plug the number of moles into the ideal gas law. So to convert grams to moles, we divide the number of grams we're given, 52, by the mass of nitrogen gas, N2. Look it up on the periodic table. Nitrogen has a mass of 14, so N2 would be 14 times 2, or 28, which means 52 divided by 28 is 1.86 moles. Now we've got a pressure. We were given 1 atmosphere. We want to find the volume. We have the number of moles is 1.86. We have the temperature is 100 K, and we need the R. Since the pressure was given here in atmospheres, R is equal to 0.0821. So V equals 1.86 times 100 times 0.0821, and then that's going to be divided by 1. When we multiply that out, we get 15 liters as the volume. If an unknown gas has a volume of 25 liters in 1 atmosphere, 1.5 atmospheres and 140 degrees Celsius, what is its volume at standard temperature and pressure? Okay, so we're given, again, we've got a volume 1, we've got a pressure 1, we've got a temperature 1, and then we're not given the numbers, but we're given STP, so that's pressure 2 and temperature 2, and we need to find volume 2. So this is going to be the combined gas law. P1 times V1 over T1 equals P2 V2 T2. So I've got a starting pressure of 1.5, I've got a starting volume of 25, starting temperature of 140 Celsius plus 273, 413 Kelvin, equals pressure 2. Standard pressure in atmospheres is 1, and we're trying to find volume, divided by the standard temperature of 273. So then I cross multiply, and I've got 273 times 1.5 times 25 divided by 413 times 1, and I would find that V2 equals 24.8 liters. Okay, what is the total pressure of 250 milliliters of a system that contains 28 grams of nitrogen and 21 grams of neon at 450 Kelvin? Well, again, we're given a volume and a temperature, and we're asked to find a pressure. And then we're given a number of grams. Well, remember, we can convert mass into moles. And then we could use moles plus temperature and volume to find pressure with the ideal gas law. Okay, so first we have to find the number of moles, and the reason this is under Dalton's law is because, remember, the pressure of the gas doesn't depend on what type of gas it is. All we care about is how much gas there is, what's the pressure, what's the temperature, and what's the volume. So once we convert both of these gases to moles, we can add them together, and then we can use that total number for the N in our equation. So 28 grams of nitrogen gas has a mass of 28 grams, so that's 1 mole. And then 21 grams of neon, which has a molar mass of 20, is 1.05 moles. So 1 plus 1.05 means we have 2.05 moles. Now we can come back over and use that answer in our ideal gas law. We're trying to find the pressure. We're given a volume of 250 milliliters. In the ideal gas law, you have to use liters. So milliliters, to get to liters, you move the decimal over 3 times to the left. So it's 0.25 liters equals 2.05 moles. That was the number we got over here. Times, they don't give us a unit of pressure, so we can use 0.0821. And then that's going to be times 450K. So then we're going to divide both sides by 0.25, and we find that the pressure is equal to 302.9 atmospheres. I know it's atmospheres because I chose to use the R value for atmospheres in the equation. So that makes the unit atmospheres. Questions about density. Okay, so again, we're bringing in some from previous chapters here. We're bringing in molar mass, we're bringing in density. In a minute, we're going to do a little bit of stoichiometry, all related to the gas laws. So what's the molar mass of a gas that has a density of 4.5 grams per liter, and it's at 8 atmospheres and 100 degrees Kelvin, or 100 Kelvin? Well, okay, molar mass is the number of grams per mole. Okay, so we need the number of grams per mole. We have a number of grams. We have 4.5, but we don't have the number of moles. So what we need to do is figure out how many moles there are. Anytime you're trying to find moles with a gas law, it's the ideal gas law, PV equals nRT. Well, do I have the information I need here? I've got a pressure, I've got a temperature, and I don't have a volume, but specifically, but it says it's 4.5 grams per 1 liter. That's what that means. So I'll use 1 liter as my volume. So the pressure is 8 atmospheres. The volume is 1 liter. The number of moles is what we're trying to find, times R. Since pressure is in atmospheres, we use 0.0821 times the temperature of 100 K. So we have N equal to 8 divided by 0.0821 times 100. That equals N. When we do that out, we find that we have 0.974 moles. Okay, so now we have 4.5 grams, and we know that that is 0.974 moles, so the molar mass is the number of grams, 4.5, divided by the number of moles, 0.974, so we end up with 4.6 grams per mole. What is the density of oxygen at standard temperature and pressure? Okay, well, at standard temperature and pressure, so the molar volume, density is grams per liter. Let's start with that. The molar volume of any gas at STP is equal to 22.4 liters. So at STP, we have 22.4 liters for density. How many grams? Well, O2 has a mass of 32 grams. Oxygen is 16, O2 is 32. So if we have 32 grams in 22.4 liters, then the density in grams per liter is 1.43 grams per liter. What is the density of a gas with a molar mass of 84 grams per mole at a pressure of 5.3 and a temperature of 100 Celsius? Again, we're trying to find grams per liter. Well, I've got grams, it's 84. What I'm missing is volume. I've got grams per mole, I've got pressure, I've got temperature, I want volume. So again, anytime you've got moles, you're probably looking at pressure times volume equals nRT. Pressure, 5.3 atmospheres. that's 5, times the volume, which is what we want to know, equals the number of moles. Well, let's pick 1 mole, make it simple. 1 mole, since we know how much that weighs, 84 grams, times 0.0821, since we're in atmospheres for pressure, times the temperature, 100 Celsius, which is 373 Kelvin. All right, so the volume equals 1 times 0.0821 times 373 divided by the 5.3, and that comes out to 5.78 liters. So now I have liters. Up here I have grams, so to find the density equals 84 grams divided by 5.78 liters. When you do that math, you get 14.5 grams per liter. Okay, a little stoichiometry, everybody's favorite. How many liters of H2O will be produced at 200 degrees Celsius and 3.1 atmospheres if you start with 35 grams of oxygen? All right, so a couple things we got to do. First of all, there should be an arrow here. First of all, we need to know how many moles of oxygen is 35 grams. Well, 35 grams divided by O2, which has a mass of 32, equals 1.09 moles. So 9. And according to the equation, the ratio is 4 moles of water for every 5 moles of oxygen. So 1.09 times 4/5 equals 0.872 moles of water. That's how much we should get. The question is, what volume would I get at a certain temperature and a certain pressure? Okay, volume. Now I've got volume that I want, I've got a pressure, and again, anytime there's moles, you're talking the ideal gas law. So plug in what we have, 3.1 atmospheres times the volume. We don't know that, we're trying to find it. The number of moles is 0.0872, that's what we found here, times 0.0821, since pressure is in atmospheres, times 200 Celsius, which is 473 Kelvin. Do that math out, divide by 3.1, volume equals 10.9 liters. Okay, diffusion. The rate of diffusion is equal to 1 over the square root of the molar mass of the gas. So we're really just basically comparing how much mass the gases have, and that goes into figuring out the rate. How much faster will hydrogen diffuse than helium? Well, the rate is equal to 1 over the square root of the mass. Well, the mass of hydrogen is 2, and the mass of helium is 4, so 1 over square root of 4. So you've got 1 over the square root of 2, and you've got 1 over the square root. Well, 1 over the square root of 4, we know that, that's easy, that's 1/2. And the square root of 2 is 1 over 1.4. So really we've got, what's 1 divided by 1.4? That's 0.7. 1 divided by 2 is 0.5. So 0.7 divided by 0.5 equals 1.4. So the hydrogen will diffuse 1.4 times faster. So anytime you're trying to compare two gases, take the 1 over the square root of each gas, and then that'll tell you how much faster one is than the other. Okay, what are the relationships between pressure and temperature, pressure and volume, volume and temperature? Well, pressure and temperature is a direct relationship. Pressure and volume is indirect. And volume and temperature are direct. So if you were going to graph these, right, just very simply, pressure, temperature, pressure, volume, volume, temperature, The direct relationships look like that. As the pressure increases, so does the temperature. Same with the volume and the temperature. As the volume goes up, the temperature goes up. The pressure and the volume go in the opposite direction. As the pressure increases, the volume decreases. So those are the relationships between those things.